Hello. Hello, hello. Now you can hear me? Or cool. All right, sorry about that. Yeah, I think sometimes my phone hijacks my mic um automatically. And even if I specify that I don't want that, it stays connected or something. Anyway, so well, we know. So okay, so this is an easy problem. We have a size equals 50, so it's very small. So and notice that we can even get away with a cubic algorithm. So we don't have to think a lot about this one. So we could go over. We want the length of the longest, right? So we go over all the starting positions, and then J is going to be the ending position of our subarray. And now we want to know if it's sorted what nums of ij, and let's say that we're gonna pass this less than operator, or is sorted nums of ij greater than. And if any of those are the case, then we want to count this subarray. And so is sorted it's going to tell us if all the elements if I compare this with this, should be true. It should be either less than or greater than. So this passes the examples, and we got accepted. Cool. But notice that we can solve this in O of n in linear time. Because notice is if we consider the streaks, so notice that we can compare consecutive elements, right? And so yeah, let me draw a little bit. So we have 1, 2, 3, 3, 2. So notice that if we compare consecutive elements, you can say, so let's say that we're only considering strictly increasing. So we consider these two elements. So this is true, it's increasing. And here it's also true, it's increasing. But here it's false. And here it's also false. It is, and if we do the same, and if we group consecutive streaks of true, then that means that we're gonna get a strictly increasing subarray of size 1 more than the consecutive pairs, the number of consecutive pairs. So there's a way in Python to group streaks, which is called group by. So maybe we can use that. So we want to get the longest streak using the less than operator and the longest string using the greater than operator. Okay, so now we want this. And so we can use the, like I said, we can use the group by for all. Yes, but here we want to compare so yes, these are the indices. So here we want to compare a of I with a I plus 1. All right, so now we go over all the groups, and if B, so if the, no, if K, so if it's true, like I was saying here, if we have a group of true, then we want to know what the length, what the size of the group is. So we do this, and now we get the maximum. We get the maximum of this. But there could be, for example, when we had all threes, there was no true. So this could be empty. So in that case, we want to default to 0. And we want to add 1, because remember that the number of consecutive pairs was 1 less than the number of elements in the subarray. So this should work, and this is linear time. It's a little, I think this line might be a little complicated, but I explained it, so should be okay. And yes, we got it. 50 milliseconds. And so as you can see, it's much faster than the previous one, than the n cubed solution. So makes sense. Yeah, I think that it is a good idea to think about when you think about some value applied to the consecutive elements. You should think about elements placed between the elements. That's usually a clear picture for me. Anyway, so let's go to question 2. Lexicographically smallest string after operations with constraint. You're given a string s and an integer k. Define a function distance between two strings of the same length n, such as the sum of the minimum distance between s1 of I and s2 of I. Hey, Creepypasto. Hey, good night. When the characters from A to C are placed in a cyclic order for all I in the range. Okay. Yeah, so here it's clear. So from A to C, you have a distance of 2. but from B to D you have also distance 2, so the total is 4. But here from A to C you can go, so this is the minimum distance, so you can go, you can get go forward 25 steps, or you can go backwards in only 1 step. So that's why it's 1. So you can change any letter of S to any other lowercase English letter any number of times. Return the string denoting the lexicographically smallest string you can get after some changes, such that the distance from S to T is less than or equal to K. All right. So here we can get A, and C. The length is 100 and K is up to 2000. Okay, so notice that we always, so whenever we have to minimize the lexicographical order, you want to go from left to right, and you want to first get the smallest value that you can for the first element, right? It doesn't matter. It doesn't make sense to get if you can get an A, for example, you should get an A. It doesn't matter how much it costs, because if you get something worse than an A, something greater than an A, then you would have gotten smaller lexicographically by getting an A. So you always try to get an A or the smallest letter that you can get at each step. So we go from left to right, and we check, we try to get an A, right? So we want to know what the distance is to A. So that's going to be either going forward from A to our current character, right? So this is going forward, or we want to go backwards, and going backwards is, so well, here we should have the ord of A. Going backwards is subtracting this number from 26, right? So it's going to be ord right. So if we go from A to C forward, we get 26 minus 1, or no, 25 minus 0, which is 25. And if we subtract that from 26, we get the distance going backwards. So we of course want to minimize the distance, and so now we know what it costs to go to an A. So do we have that many? So if the distance is greater than K, then we cannot get to an A. If it is not greater, then we can get an A. So then we just append A to the result, and we subtract this from K, right? But if we can we want to get the smallest that we can. So then we want to subtract k from our current character, and that is the character that we will add, and then we're done. That's how many we used all the operations that we have available, and so then we finally join into a string, and here yep. All right. So yeah, I think this one was pretty straightforward. Yeah, every time you get the lexicographically smallest condition, then you know you can be greedy in a sense. You have to minimize at all costs at each position. And then things can usually become easy. Anyway, so let's go to Q3. Minimum operations to make median of array equal to k. You're given an integer array nums and a non-negative integer. In one operation, you can increase or decrease any element by 1. Return the minimum number of operations needed to make the median of nums equal to k. Oh, I think this was added. Yeah, many people complained that it was not specified in the description. This was missing. So what I did was to look at this example. Here it is clarified because so here this is an even length array. These are the two middle elements, but k, so 4 is the median, and so here is the larger element, which if you think about it, this is just if you sort, and so here the length of the array is 6, so if you divide by 2 you get 3, so this is 0, 1, 2, and 3, so it's just the size, the 0 index of the size divided by 2. Okay. So I guess we can just get the median. We sort nums, and then this is the median. And now notice that if k is greater than the median, then we have to decrease its position so that it becomes the median. And to decrease its positions, notice that the elements that are greater than it don't matter, and the elements that are less than the median also don't matter. We have to increase all the elements from the median up to k. So let's start coding this. So if the median is less than or equal to k, that means that we need to increase all the elements from the median on. So let's say, so this is where the median is. So while this is less than k, well, no, this is less than and nums of I is less than nums is less than k. Yes, in that case we want to add to the result the difference between k and nums of I, because we have to increase this number up to k, and we increase I. Okay, and then in the other case we have, it's the same thing, but we have to go backwards. So while I is greater than or equal to 0, and nums of I is then in that case we want to decrease the numbers yes, we want to decrease the numbers and we want to subtract this, and so here we return res. All right. Cool. So yeah, maybe I could have avoided this duplication, but yeah, I guess it doesn't matter. I mean, especially in a contest. So let's go to Q4. I like this problem because I think I'd be lost at first, but then seeing it that way makes it simple. Yeah. Yeah. Seeing it what way? I mean, you can classify the elements. So when you assume this, then it's pretty clear that it doesn't do anything to increase the numbers. I mean, I think when you see it, I mean, from the POV of the current median, right? Okay, so let's do Q4. Minimum cost walk in a weighted graph. There is an undirected weighted graph with n vertices labeled from 0 to n minus 1. You're given the integer n and an array edges where, okay, so this is a weighted graph as usual. And here where we get the definition of a walk, which it's different than a path, than a simple path, because you can repeat nodes and edges in a walk. And then the cost of a walk starting at node U and ending at node B is defined as the bitwise AND of the weights of the edges traversed during the walk. In other words, if the sequence, okay, so it's a NAND, and you're also given queries. You need to find the minimum cost of the walk starting at vertex S of I and ending at vertex T of I. If there exists no such walk, the answer is -1. So, okay, so if there exists no such walk, that would depend. So if they are not in the, so that the graph is not necessarily connected. So if the nodes are in the same connected components, then you would have a walk. So you only want to respond -1 when they are in different connected components. And notice that you're asked to minimize the AND, and if you know the properties of the AND, bitwise AND, notice that you never, when you add one value to the AND, you can never increase the value. You can only decrease it, or it stays the same. So that means that you want to add as many edges as you, all the values of the edges that you can. And if the within a connected components, you can walk over all the edges, right? All the edges are reachable. That's the definition of a connected component. So here, the optimal, so to find the minimum, you have to traverse every single edge of the connected component. That's going to give you the minimum. And so this boils down to just going over finding the connected components and then doing the AND of the whole of all its edges and returning that for the queries. So let's just do that real quick. So we first go over the edges. So we create the adjacency list. And then we are going to, so the number of components is going to be M, and we're gonna have the ID of the component for each node. Let's set it to -1 at the beginning. And now we're gonna do a BFS. So we need a queue. And well, first of all, we need to determine the beginning, so the source. So if the index of the source is -1, it means that we haven't visited the source. So now we start the BFS. So the index of the source is going to be M, and at the end we're going to increment M, so because we found a new connected component. And here we start from the source and we pop, we go over the adjacent nodes, and we want to also, for each connected component, we want the AND of all the edges in the component. And we are yeah, this is not size M actually. And yes, and we want to initialize it to a mask with all ones, right? Because that's going to that's the neutral element of the AND. So the mask, and we know that the numbers are up to the values, the weights are up to where is it, 10 to the 5. So I think that that is 2 to the 17. It's greater than 10 to the 5. So this is going to give us all the ones that we need. And so here, when we start a connected component, we are going to add here an element with a mask. And we want to here, when we visit an edge, we want to AND this connected component with the weight. And if the index of B is -1, hello Flavio, welcome. Here we set this to M and we append it. Okay, so now we have all our connected components and we have all our ANDs, and so now we can go over the queries. Is it queries? Query. And so here, so there is an edge case here, because if they are the same, if the start and the end of the walk are the same, I think you have to return 0. This is not it should be specified here, but it is not. So you might get a wrong answer. So if the connected component, the index of the connected component of S is equal to the index of the connected component of T, then that means that we want the AND of that connected component. And otherwise, if they're not the same, then we cannot walk from one to the other. So we return -1. And so I think this handles everything. Yep. And we got it. Beats 98%. That's pretty good. I think we are far from the heap here. So yeah, I think this was pretty straightforward. Nice. Good job. Thank you, guys. So yes, I think this one was pretty straightforward for a Q4. I mean, you needed to understand the property of the AND to realize that you always want to walk over all the edges. That's going to minimize the AND. And so once you know that, it's just detecting the connected components So there's not much to it after that observation. So yeah, that's all I think. So it's 40 minutes. Yeah, it wasn't the hardest. So 40 minutes sounds good. So yeah, thanks for watching and see you on the next one. Bye bye.